Magnetic lift. A magnetic lift uses a cylinder with radius r and width w wrapped by conducting wire capital N times on a diameter as shown in figure. So this is a cylinder radius r and the width w. We have n turns of a coil wrapped around the center of the cylinder. A uniform external magnetic field B points downward while current I flows in the sense indicated. So this is basically flowing like this. A mass M is hung from the cylinder by a cable attached to its rim on the axis of the coil. So this coincides with the axis of the coil. The height above the lowest possible position of the mass, this vertical position, is h. Part A, what is the minimum current I for which the mass can be suspended with h greater or equal to r? So when h is greater or equal to r, we have this is going to be past this point, it will be going up. And what is the height of the mass when the cable attachment rotates 1/2 turn to the top of the cylinder in terms of r? Okay, now this is our x-axis, y-axis, and z-axis coming out, and we see that this mass feels the gravitational force mg pointing down, tension pointing up. This tension becomes a tangential force as soon as h goes above r. Why? Because then it will be wrapped around the cylinder, and you can see that mg will be balanced by tension, and this tension is going to be a tangential force. So you can see that the position vector with respect to the rotation axis will have a magnitude capital R here, making an angle 90 degree with tension. And let's say that the magnetic moment mu and the magnetic field B makes an angle phi in general, according to this figure. And we can write the magnetic moment magnitude as the total current, number of turns times I, multiplied by the area A of the coil. So A is area of the coil. And what is that area? Because we have one side twice the radius, the diameter, one side is the width, so this is a rectangle. It's going to be 2r times w. So this will be ni 2r w. That's the magnetic moment. What is the torque due to this magnetic moment? It is the cross product of magnetic moment with magnetic field, and that torque will have a magnitude, the magnetic moment 2nirw multiplied by magnetic field B multiplied by sine of the angle between them, so it will be sine phi. And what is the direction of this torque? Tau mu is in which direction? So let's see. The magnetic field is on the xy plane, pointing in minus j hat direction. The magnetic moment mu is in the yz plane, pointing in this direction. So using our right hand, if the four fingers of the right hand point in this direction, and then we curl them towards minus j hat direction, the thumb points in minus I hat direction. So tau mu, the torque due to the magnetic moment, is in minus I hat direction. That's what we observe. At the same time, the mass is to be suspended, so the net force on the y-axis should be equal to 0. The tension must be balancing the gravitational force mg. And what is the torque due to this tension? It is r cross f. So if I look at the position vector, for example, here, the position vector r will be this vector, r vector. R cross f basically gives me, r cross f gives me plus I hat direction. Why? Because the plane that I have that I see this. That's from the side view. That's the YZ plane. So if you look at R cross F with the right hand, so we four fingers of the right hand point in the direction of this position vector R here to the point of application of the force, and cross F we find that this torque is in plus I hat direction, and because of the 90-degree angle we have R times mg in plus I hat direction for this torque. Okay, and if we have equilibrium, at equilibrium, we need to require that the net torque is equal to 0. So the torque due to the gravitation is mgr. The torque due to the magnetic moment, magnetic field interaction is 2 nirwb sine phi. The r's will cancel here, and I will find the current that is required to be mg divided by 2n wb sine phi. Now this current is to be minimized, so we can see for which angle this will be minimized. For minimum current, we require a maximum sine phi, so that means phi has to be equal to 90 degrees, so that sine phi is equal to 1. So phi is equal to 90 degrees implies also that h must be equal to capital R, right? So when phi is equal to 90 degrees, this is basically going to be pointing in this direction. So the coil will be totally up like this. If it is totally up like that, then we're going to have this at a distance r with respect to the background. So this will be the proper position with respect to the ground here. So this distance will be equal to r. All right, so that means in this picture here, this is the position we are looking for, but when you rotate it beyond this point, actually these coils are placed more like this. Okay, so basically we are moving from this position towards this position, so that phi is equal to 90 degrees, and so that this mass will come down and it will be h is equal to r. That's when we have the minimum current requirement satisfied, and that minimum current is equal to mg divided by 2n WB. This is our minimum current in part A. Now part B asks me, what is the height of the mass h top when the cable attachment rotates 1/2 turn? So when the cable attachment starts turning, this is h is equal to 0 position. If I have quarter of a turn, this will go up, so h will be equal to r. If I go another quarter of a turn, then this will start wrapping around, and the decrease in the length of the cable will be equal to the quarter of the circumference of the circle. So in the second stage, so this is the first, this is the second stage. In the second stage, the reduction in the hanging cable length hanging cable length will be equal to quarter of the circumference, which is pi r over 2. Therefore, I will see that for half a turn of the cylinder, h top, the new position, will be equal to capital R plus the second stage pi r over 2. So this will give me capital R times 1 plus pi over 2. So that will be the position of the mass. Okay, so in part A, we were required to find the minimum current for which the mass can be suspended with H greater or equal to R. So first thing I noticed that when H is equal to R, I will have this position here. The coil will be completely vertical, and this will be right at the position vector will be parallel to the x-axis for the application point of the force, and I will have a torque Rmg, mgr. But when I start wrapping this more, so h goes beyond r, so this mass is lifted more, I will see that the tension that will appear at this point, so there will be a decrease in the cable length, and the tension that will appear at this point will be a tangential force, so it will have the same torque mgr. So that torque mgr, due to this gravitational force or due to this tension, must be balancing the torque mu cross b. So what is mu cross b? It is the magnitude of the magnetic moment, and I times area, which is 2rw, multiplied with magnetic field, sine of the angle between them, sine phi. So mgr must be equal to 2nirwb sine phi, and the current is then mg over 2nwb sine phi. When is the current minimum? When phi is equal to 90 degrees. So that means at this position, when the coil is is in the vertical position, and you can see that the mass is going to be the height will be equal to r, so that the mass will be hanging like this directly from this end point here. So that means the tension will be pointing down like that. With that, I find the minimum current to be mg over 2nwb. If I allow the cylinder starting from h equals to 0 to have a half turn, so if there's a quarter of a turn here, I'm going to reach h is equal to r. You can see that from this figure. So basically it's turning with it. There's no wrapping until I reach h is equal to r. When h goes beyond r, it starts wrapping around, and when I reach the half turn, it's going to be a decrease in the length of the hanging cable by 2 pi r divided by 4, so which is pi r over 2, so that the new h value from the ground will be capital R plus 2 pi r over 4, which will give me capital R times 1 plus pi over 2.